Okay, we're going to review one of the questions that we had in the test yesterday. This question was adapted from your textbook, Brown and Others, 10th edition. It's a question from chapter 3, number 88. I just adapted the question slightly. I removed some of the extra words and I doubled the quantity. So I said 2.1 grams instead of 1.05 grams is burned, and of course you double all the other quantities. So vanillin contains carbon, hydrogen, and oxygen. When 2.1 grams of it is burned, it produces 4.86 grams of carbon dioxide and 1.0 grams of water. What is its empirical formula? Its molecular mass is 152.14. What is its actual formula? And then I gave you the pieces of information that you needed to solve it. Here is the solution to the problem. We first of all represent the chemistry of a combustion reaction. I put letters here to represent unknown numbers. I don't know what the numbers for the formula of vanillin are, but I do know that when you combine it with oxygen, you're going to get carbon dioxide and water. And we're told we get 4.86 grams of carbon dioxide, so we're going to divide by the molar mass of carbon dioxide, find out how many moles of carbon dioxide is produced, and since we find out how much carbon dioxide is formed, we also know how much carbon was in the carbon dioxide, the same number of moles, because for every mole of carbon dioxide, you're going to have 1 mole of carbon. All the carbon is coming from this molecule. So if we know how many moles of carbon dioxide we have, we will know how many moles of carbon were present in this molecule. Likewise with water. All the hydrogen that comes from here gets turned into water. Combines with oxygen to form H2O. So if we find the number of moles of H2O, we can also find the moles of H. The calculation for the moles of hydrogen is a little more complex. Well, it's got one extra step. We start off by calculating the moles of water. It's 5.5 times 10 to the minus 2. And here I displayed the number 2 different ways. I've noticed that some students aren't very comfortable with using exponents on their calculator, so I showed the number the 2 different ways that you could show it. I prefer to show it this way because it gives you the full number. If you use 0.0555, your most calculator readouts will cut it off over here. So you get a more accurate number, representation of the number if you leave it in exponential form. Either way, you'll get the same answer in this calculation because you're only allowed, I think, about 3 significant figures anyway. Yeah, 3 significant figures, and you would still get the answer for an empirical formula calculation. But I still like to build up the habit of not making rounding errors all through the calculation. And that's why I retain all the decimals. Anyway, we have that many moles of water. If we multiply by 2, we get the number of moles of hydrogen. Then from the moles of hydrogen, we multiply by the grams per mole mass of the hydrogen to get the grams of hydrogen, which is 0.1118. So we found the grams of hydrogen, we found the grams of carbon. We take these 2 numbers now and subtract them from the original amount of the sample, the mass of the sample. So 2.1 minus the mass of carbon and the mass of hydrogen is going to give you the remainder, which is the mass of oxygen. We then took the masses of each one of the elements present in the molecule, divided by the molar mass, and it gave us the moles of each element present in that sample. Then we divided by the smallest number of moles in the sample, we see 4.13, etc. And we got this proportion, 2.67, 2.68, and 1. Now you can't have an empirical formula with fractional amounts of atoms in them, so we have to multiply these numbers by a whole number value that will result in whole number atom amounts. And we found out that multiplying 2.67 by 3 gives you 8. And the resulting empirical formula is C8H8O3. When you calculate the empirical formula weight, represented here by DFW, you get 152.14 grams per mole. We were told in the question earlier that the molecular mass of the actual molecule is 152.14. So because the actual formula has an identical molecular mass to the empirical formula weight, we can say that the actual formula is the same as the empirical formula. We get C8H8O3.